Welcome to The Explainer. You ever wonder how we can predict, like, the exact path of a planet years from now? Well, it all starts with a much simpler question, one that the great physicist Richard Feynman loved to explore. How do you even describe the motion of a car? Today, we're going to follow his exact line of thinking and see how cracking that one simple problem basically gives us the keys to the universe.
It really all comes down to this one question. What does 60 miles per hour actually mean? Right now, at this very instant. I mean, if you've only been driving for a minute, you definitely haven't gone 60 miles. So what is that number even talking about? And believe me, this isn't some new question. It's a puzzle that's been stumping people for centuries. The ancient Greeks totally got tangled up in this. You've probably heard of Zeno's paradox about Achilles and the tortoise, right? If Achilles keeps having to cover half the remaining distance, and then half of that distance, and so on, he has to cross this infinite number of tiny gaps. So how does he ever actually catch the tortoise? It's a seriously mind-bending way to show just how tricky it is to pin down what's happening in a single, perfect moment in time.
So you see, this isn't just a fun little brain teaser. It's a major roadblock. If we can't describe with perfect clarity how something moves from one instant to the very next, then how on earth are we supposed to figure out the fundamental laws that run the entire universe?
And this is where Richard Feynman's approach is just so smart. Instead of getting lost in all the philosophy, he was incredibly practical. He basically said, look, forget about defining speed for a minute. Let's just start by describing what we see. Let's just describe the motion. All right, so let's do it. Let's follow Feynman's lead and just track a simple car ride. We're not going to use any fancy physics or anything yet, just a stopwatch and the car's odometer. We're just collecting the raw data. And this is what we get. At minute 0, we're at 0 feet. After 1 minute, we've gone 1,200 feet. 2 minutes, 4,000 feet, and so on. Right now, it's just a list of numbers. It's a factual record of the trip, sure, but on its own, it doesn't really tell us a whole lot. But watch what happens when we turn this boring table into a picture. You plot it on a graph, and bam, all of a sudden, a whole story just pops right out. You can literally see the car speeding up at the beginning. Then it slows way down around the 4-minute mark, probably hitting some traffic, and then it takes off again right up until the end where it just slams on the brakes. And why? Well, as Feynman puts it in his lecture, the car was stopped by a cop. So this graph brings us right back to the main puzzle, doesn't it? Looking at that curve, what was the car's exact speed at, say, the 7-minute mark? And this is where Feynman uses this fantastic little thought experiment to show why that question is so tough to answer. And you know what? She's got a point, a really good one. The very unit, miles per hour, suggests a full hour of time. If she's only been on the road for 7 minutes, how can you even apply that measurement to her? It feels illogical. So the cop tries the standard explanation, right? Well, it's the speed you would have gone in an hour. But she shuts that down immediately. She points out that if she had kept going like that, she would have crashed right into a wall. So that whole hypothetical would-have thing, it doesn't work either. We need something better. And here it is, the big idea, the huge breakthrough from thinkers like Newton and Leibniz. They said, forget about measuring over an hour or even a minute. Let's measure how far the car went in just 1 second and calculate the speed. Then let's do it again, but over an even tinier slice of time, like a millisecond. As you keep shrinking that time window, smaller and smaller, getting closer and closer to 0, you'll see that the speed you calculate starts to settle down. It zeroes in on one single, stable number. And that number, that's your true instantaneous speed. And that whole process we just described, that idea of finding the limit of something as an interval shrinks to nothing, well, that has a name. It's called differential calculus. This entire powerful branch of mathematics was basically invented to solve this exact problem. It finally gave us a language to talk about rates of change moment by moment. Okay, so we solved the ancient puzzle. That's pretty cool. But here's the thing. This new tool, calculus, is so much more than just a riddle solver. It's the key that unlocks a whole new level, moving from just describing what already happened to actually predicting what's going to happen next. And this is where it gets really, really powerful. Think about it. If we can use calculus to find the rate of change of position, which we now call velocity, what happens if we just do it again? What if we apply the exact same method to velocity itself? Well, we can. And that number, the rate of change of velocity, has a name too. We call it acceleration. It's kind of like the speed of the speed. And this is the moment where everything changes. This is the giant leap. Newton's second law, F equals ma, provides the critical link. It says that if you know the forces acting on an object, like gravity, then you automatically know its acceleration. I mean, just stop and think about what that really means. That little equation is basically a bridge from the past to the future. Before, all we could do was look at our data and describe how a car had moved. But now, with F equals ma, if we know where something is right now and what forces are pushing or pulling on it, we can calculate its acceleration, and from that, we can predict exactly where it's going to be a moment from now. So, just how powerful is this new predictive machine we've built? All right, let's take the exact same step-by-step logic we just used for the car, and let's go big, like cosmic scale big. It's literally the same process as the car problem, just with bigger numbers. You start with the planet's current position and its velocity. Then you use Newton's law of gravity to figure out the force acting on it. That force gives you its acceleration. The acceleration tells you its new velocity a split second later. And that new velocity tells you its new position. And then you just do it all over again. And again, and again, step by tiny step by tiny step. So you run this simple, almost boring calculation millions of times, and out of this gigantic, messy spreadsheet of numbers, something absolutely incredible emerges. When you plot all those little data points, you see a shape. The chaos traces out a perfect, elegant, and completely predictable ellipse. You've just calculated the orbit of a planet from scratch. And get this isn't just a thought experiment. As Feynman pointed out decades ago, a modern computer can run all of those tiny step-by-step calculations for Jupiter's entire 12-year orbit, even factoring in the gravitational tugs from all the other planets, in about 2 minutes. So just think about the journey we just went on. We started with a seemingly impossible question about a car's speed, and by solving that one little puzzle, we stumbled upon a method so powerful that it lets us map out the entire intricate, clockwork dance of our solar system with breathtaking accuracy. And that really leaves us with this final, amazing thought. We went from a simple car ride all the way to the cosmos, all because we finally found the right language to describe change. It just makes you wonder, what other enormously complex systems out there, from the weather to the stock market to the firing of neurons inside our own brains, are just sitting there, waiting for us to discover their simple underlying rules?